11.2 is going to start talking about this idea of area, which we're going to spend quite a bit of time in chapter 11 about. You're going to see stuff with the angles we talked about on 11.1. But notice the title. It's going to focus on a certain type of figure that we're finding the area of. It says finding the area of a regular polygon. So let's just do a quick recap. What is a regular polygon?
Regular polygon means that I have all congruent angles and all congruent sides.
Okay. So if you read the first example, it says find the area of an equilateral triangle with a side length of 8. Now, it says find the area of an equilateral triangle. Is an equilateral triangle regular?
Yeah, well, we know all of the sides are the same. They're congruent. That's what equilateral means.
Okay.
And when all the sides are congruent, that we talked about the base angle theorem. Converse talked about base angle theorem, the corollary to that, showed us that all the angles were then all congruent as well.
Now,
so that's something we've explored before.
Is that with any regular polygon, if all the sides are congruent, or I shouldn't say any polygon, if the sides are congruent, does that automatically mean the angles are congruent?
No.
No. Because, for example, like a rhombus has congruent sides, but not all the angles are congruent. This is just unique because it's a triangle. Imagine that. Triangles are kind of special.
We do love them.
Here's the deal. This is actually nothing new, this first example. So I'm going to ask you guys to go ahead and answer this question, pause it, and then check your answer with us in the end, okay? Because this is something we did in chapter 9.
Okay, so to find our area for our equilateral triangle with side lengths of 8, so we're going to go ahead and mark, at least, do just the two sides. On those sides is 8. Because when I'm thinking for area, I know I need 1/2 base times height. So let's draw in an altitude.
Okay.
And with that altitude, we know when all the angles are congruent, they were all 60. So I'm thinking 30, 60, 90 triangles.
So these are 30, 60, 90 triangles. So if you kind of think about it, let me just pull this out. That's why this is coming back from chapter 9. So this is a 30, 60, 90. Now, this is
8.
8.
And that's the hypotenuse. So that makes the shorter leg half of that, which would be 4.
And we also explored in any equilateral triangle, the altitude bisects this. So these are each little guys are little 4. Okay?
Right. Okay, and then we knew that the height there, that altitude, would have been a 4 radical 3.
So that's your height. Now, how do you find the area of an equilateral triangle?
1/2 base times height.
So it would be 1/2 the base, which is...
So the whole thing of 8.
So this is your base. I'm
Be
going to make a
careful.
note of
Make
that.
sure we realize it's not the 4.
Times the height.
Times the height, which we said was 4 radical 3.
So the area is going to be, what?
16 radical 3.
Okay. And it doesn't have units, doesn't say round, so we're just going to leave it exact.
Sounds good.
Now, here's what's really cool, is that if you haven't noticed already, when we do the area of equilateral triangle, the process is all this like the same every single time. Okay? We know if they give you the side length, we can kind of find some missing pieces here. So we're going to explore this idea, all right, on this next slide. All right? I'm going to have Ms. Hokerby talk us through this one.
Okay. So on this one, we could kind of think about our process. We said we took, to get our base, we did half of the base, so half of our S, right? So just talking about our formula for area. Half of the base times, and when we talked about our height, that height involved doing, really, because this, would you agree that this little piece, just to get for the one
is
little right
half
triangle,
of a side length.
so half S for just this piece. And when we talked about to get for the 30, 60, 90, to get from that piece, from that shorter leg to the longer leg, we took that times what?
Radical 3. So if you go back a slide real quick, let me just kind of compare what she's doing here. So for example, if we knew the whole base or side length was 8, half of that was 4. So that's that little guy down at the bottom here. And then the height was just taking that half of that side times radical 3. So that's what she's doing. She's taking, to get the height, half of the side length times radical 3.
Okay, so when we do our formula for area, we do half of the base.
And the base is your side length.
Base is the whole side length times the height. And our height we did 1/2 S radical 3. Okay, so this is 1/2 base times height.
Okay.
Okay.
Now we can probably simplify that down a little bit.
Yeah, and when we're multiplying, we know that we can multiply all the whole parts together, and there is no other radical, so it's going to have a radical 3 at the end. And I can also take the numbers times each other.
So a half times a half would be a fourth. And then side times side would be side squared.
And we still are going to have our radical 3. This right here is actually the formula that we're going to be exploring. When we're given a side length, We don't even have to break it in and talk into a little triangle and talk about the 30, 60, 90. We're able to just go, when we know a side length.
Of what kind of figure?
Of an equilateral triangle, yes. Then we can go ahead and put that side length into this formula. 1/4 side squared radical.
So let's test it with that last one real quick.
Sounds
the
perfect.
side length was 8. So if I use the 1/4 side squared radical 3, so 8 squared is 64. A fourth of 64 would be 16. So it would just be 16 radical 3 would be the area, which is the same thing as we just got.
Absolutely.
I kind of like that approach better.
It's nice to know these formulas. Now, guys, realize that you can go the longer approach to do this, but you're going to like to have these shortcuts.
Yeah.
We're going to learn some formulas this chapter that are going to be extremely helpful for you.
So make sure you write it down. Yep.
There is a theorem that goes along with this, and it's the area of an equilateral triangle. It only works for equilateral triangles, not for just any triangle. And it says that the area of an equilateral is 1/4 of the square of the length of the side times radical 3. So area equals 1/4 side length squared times radical 3. So it's just that's the formula, and that's what the theorem tells
Now,
us.
can you, when I think a fourth of something, that's the same thing as dividing by 4, right?
Sure.
So could you write it as side squared radical 3 divided by 4? Would that get you the same outcome?
Absolutely, because we know that when you're dividing by 4, you wouldn't divide the radical by 4 because they're not both radical parts.
So it just depends. Sometimes some of you might like that approach better, okay? All right, so guys, I want you to keep in mind, finding the area of any triangle is just 1/2 base times height. So we can still use that approach. But because an equilateral triangle is very unique, we could actually find the area of it with this new formula. So when you see area of an equilateral triangle, I'm going to encourage you to think that new way, that 1/4 side squared times radical 3. I'm going to encourage you to do that. So this is one I want you to try on your own because I think you can handle it. So go ahead and try it, pause it, then try it, and then check with us. All right. It says we need to find the area of an equilateral triangle with a perimeter of 12 inches.
Okay, so now we've got the idea of perimeter in here also.
So perimeter basically means what?
Add up all the sides.
All
So
right.
if I've got 3 congruent sides, I just really want to divide that by 3 to get the side length.
So that's going to get you a 4 for the side.
Perfect.
Okay. Now, knowing the sides of an equilateral triangle, can we use this formula?
Definitely.
Now, if I don't give you
Absolutely.
the side, if I give you the height,
It's not going to work.
it's not going to work as convenient. So this formula only is nice when given the side. So let's use that formula. We're going to try that. So it'd be 1/4, or you could just divide by 4, times your side, which is 4 squared, times radical 3. Okay, so I often do the squared part first. Think order of operations. Square the 4,
Definitely.
you get,
16.
and then a fourth of 16 is
4.
So it'd be 4 radical 3. Now, there are units. So do you think we'd want a rounded answer possibly?
Probably want a rounded answer on
Now,
this
if
one.
it doesn't tell you how to round, I usually just do 2 decimal places.
That's what I do
That's
too.
usually the consistent. What are we getting about?
So we get like 6.9282, etc. So 93 would be a good way to round that.
And this is inches squared.
Yeah, don't forget
Right.
we're in an area, so
Okay, so this is the rounded. This right here is the exact answer. So if there's units, go ahead and round because that's a more realistic answer.
Yeah.
Okay, now here's the deal. We are not going to just talk about equilateral triangles.
Right.
There are lots of regular figures out there. So I'm going to have Ms. Hogarby kind of talk about some of the vocab that will lead into where we're going.
All right. So first of all, you're going to notice that we have a circle on this page. And we're talking about polygons. Circles are not polygons.
No.
I don't want to confuse you. But there are parts of a polygon that make sense. They make more sense when we see it in context of the circle that is circumscribed around it.
Okay, what do you
Okay.
mean by that? Circumscribed around it.
Circumscribed means that it's this polygon that I have, any polygon that I draw within a circle where its vertices are touching the outside or the sides of the circle.
Okay,
So
or
it's the
parts of the circle.
part of the circle. Yeah. So they're going to have the same center.
Okay.
Okay, so the center of the circle is also the very center of this regular polygon. And I want
Okay.
to emphasize again, This is with regular polygons that we're going to be talking about. And the radius, this is a term that we're used to seeing with circles, but the radius of the polygon is the same as the radius of the circle. Now, when you think about a radius, we know that we could draw in a radius lots of different places within a circle.
Yes.
The only place that you can see that radius actually touches the polygon itself also is where, though?
At the vertices.
At the vertices. So this would be considered a radius.
And a lot of times we label the radius with a lowercase r.
You got it. Just like we normally do with a circle. Okay? So this is also the center. I just want to emphasize that. I don't want you to think that I'm drawing in a special line here, but this point right here is still my center. All right, now, when we think about it in terms of those two pieces, we've got some other special relationships that you're going to notice.
Okay. Some new words.
Some new words. The first word is apothem.
Okay.
Which, my students always laugh and they say, it sounds like a possum.
Yeah.
It's an apothem. It is a weird word, I agree.
Yes.
And it is the distance from the center of your polygon to any side of the polygon. Now, I want you to think for a minute. When we talk about to a side, we're not talking about to a vertice anymore. So it's not the radius.
Okay.
But it goes from that center to the side. And we know that the shortest distance between 2 points is always going to be the what distance?
It has to be perpendicular.
Right. So when we draw in the apothem, it should be perpendicular to our side.
So you might make a little note to self under that apothem. And we usually use A for apothem.
Yep.
But you might, guys, you might make a note to self that under apothem it's perpendicular to a side. And here's the deal. You could draw the apothem anywhere, right? As long as it's perpendicular side. What do you think is going to be true anywhere I draw that apothem compared to all the other apothems you draw in?
They should all be the same because this is a regular figure. And that's what's special about regular figures.
Just like the radius. If I draw the radius to any of those vertices, they're going to be the same distance.
Right.
Okay.
Okay. The other thing that we talk about is called our central angle of a regular polygon. And it's an angle whose vertex is the center.
Okay.
So that's important. The vertex of the angle is at the center. And whose sides contain 2 consecutive vertices of the polygon.
Okay.
Now, I want you to think about this one, okay? We are going to draw in, we know that it goes from the center. We want an angle, so we're going to actually need 2 segments here.
To a vertex.
To a vertex. So if I draw in one here, where would my other one have to be?
Well, it has to be a consecutive vertice, so then maybe right there. That would be a central angle. We could have drawn it up to the top right, okay? But as long as it's 2 consecutive vertices. Notice how she created those central angles. They're formed by 2 radii.
Yeah.
And they're 2 radii that are consecutive. So it's not going to be like one of those radii and then the one that's in yellow because those wouldn't be consecutive.
Exactly. Now, what do you notice? How many central angles could I have actually drawn in here?
Well, in this one, since this is a hexagon, we could draw in basically 6 different radii. So I would have 6 central angles.
Right. If I draw in, and I'm going to do it in pink just so I don't confuse you with what else I've got here. All of the, to any radius, as long as you're doing consecutive vertices, those are all central angles. This would be, and they should all be what?
Congruent, because this is a regular polygon.
So how do you think we could find that measure of the central angle?
Okay, well, I'm thinking, I love that you drew them all in, because when I see all of them, they're all congruent, and they all create a full 360 degrees, because they make a full circle.
Absolutely.
So if I can take the 360 and divide it by how many of them I have. And I'm going to have 6 in this because there are 6 sides. So I'm going to divide it by number of sides. So n.
Perfect. That looks like another formula we've seen.
That helps you find one exterior angle of a regular polygon, too.
Yeah, I don't know what I'm doing. I heard exterior, so I started writing an E. No, that's true. So the central angle is also the same formula as the exterior angle formula. Central angles would be 360 degrees divided by
and guys, you're going to need to know that idea. It's not a hard idea, but just remember 360 divided by number of sides gives you the central angle.
Okay. Now, I want you to notice when we drew in the apothem and when we drew in a radius, they kind of help form something that we've seen before.
A right triangle.
A right triangle. And we're going to be using those pieces a lot.
Okay.
So now we've pulled just those specific.
Now here's the deal, guys. We know how to find the area of a regular triangle, which is the equilateral triangle. But not all regular polygons are going to be triangles. So this slide, and I want you to stay close with us here, we're going to explore a way to find the area of any regular polygon. So even a triangle. If you could use this formula we're about to explore for a triangle as well. All right. I wouldn't necessarily encourage that because the formula for area of a regular triangle is a lot easier.
Right.
Okay. Now, what I want to keep in mind, I'm using the same picture from the last slide just to kind of use a reference. Now, not all regular polygons are going to be hexagons. Okay. We're just using a hexagon here. One thing to keep in mind, I'm going to go back a slide. I love Ms. Hograby's drawings here. Notice that in the regular hexagon or any regular polygon, when you create all those radii, you create several triangles. And what do you think is going to be true about all of these triangles in general?
Well, if it's regular, they should all be congruent. They would all have the same central angle. They all have the same base. They all have the same apothem. They all have the same radius.
So if I could find the area of one of these triangles, then I know the area of all of these, and I could just add them all up, right?
That sounds good.
So I want you to keep that in mind. So our focus, this is our goal, all right? Our goal to find the area of a regular polygon. We're going to find the area, if I can write this, of just one of the triangles, okay, of one triangle, and then we're going to multiply it by how many triangles you're going to get. Now,
that's also the same as the number of sides.
so the number of triangles, which basically means the number of sides. Okay, because in a hexagon, there's going to be 6 of them. If it was an octagon, there's going to be 8, so on and so forth.
Right.
All right, so let's talk about the area of just one triangle.
Okay. So we know this is not necessarily, it could be an equilateral triangle, but not necessarily an equilateral triangle.
Okay.
They will always be isosceles triangles.
And why is that? Because
the radii
are congruent. So these are always going to be isosceles. I love how you do that. So area of one triangle, this is always isosceles. All right. Now, how do you find the area of any triangle?
1/2 base times height.
Okay, so I'm going to do 1/2. What is the base labeled in this?
The side length.
The side length times, what's the height of that triangle?
Oh, the apothem.
So the apothem
is
is
the
also
height of
the
the
height
triangle,
of
not the height of the shape, but the height of the triangle. That makes sense.
So I'm going to multiply 1/2. This is my base. This is my height. Hopefully you guys are all seeing that. Times, now the number of triangles is also the number of sides. What did we use for the number of sides, variable-wise?
Well, usually we talk about n
Yeah.
for the number of sides.
So we're going to do n for the number of sides.
Okay.
Now, I'm going to do a little bit of rearranging here because with multiplication we can rearrange. I'm going to flip-flop these things. So it's going to be 1/2 times the apothem times the side length times the number of sides. Now, I'm going to focus on just this piece. If I know the side length and I multiply by how many sides I have, what are you essentially finding?
That's the perimeter.
So instead of S times N, I'm going to do 1/2 times A times, instead of this, is going to be capital P for perimeter.
Okay.
This is the formula for finding the area of any regular polygon.
Now, I do have students every year that will take the area of one triangle times the number of sides, which is okay too. This, a lot of times though, will be given, or I shouldn't say a lot of times, sometimes we'll be given the perimeter. So it's really nice to know this formula so you don't have to break that down.
So here's the deal. One reason why we kind of talk you through this process is because of what Ms. Hookery just said. You don't have to use this formula. If you want to find the area of one triangle and then multiply how many there are, that's how this came about. Okay, so there is a formula. Okay, so it says the area of a regular polygon, again, it's a theorem here, it says the area of any regular n-gon, so whatever number of sides, with the side length s. What is it? It's half of the product, so we're multiplying the apothem and the perimeter. So basically you're going to see 1/2 the apothem times perimeter. Now I want to keep in mind P is capital. If it's lowercase, it would mean it would be a side length.
Right.
Of some sort, or a length of some sort. Capital P is talking about the whole perimeter.
And capital A is area as opposed to the lowercase a of apothem.
So the capital P is the perimeter of not the triangle, of the regular polygon you're finding the area of. All right? And the polygon, the apothem is basically the height of your triangle. Okay? So just keep that in mind.
Yes.
So we're going to try some examples.
All right, and the first one that we're going to look at is talking about a regular hexagon. We've been seeing this picture kind of repeatedly, so let's talk about how we could actually find the area of a regular hexagon with a side length of 15.
Okay.
So we know that all the sides are going to be congruent. We could write 15s around all of them.
Okay.
I'm not going to do that right now.
No.
Okay. We know that area equals 1/2 of the apothem times the perimeter.
Okay.
Okay, now let's talk about which piece do we want to look for first.
Well, since they give you a side length, finding the perimeter would be pretty easy to find.
I think so too. It doesn't matter. You could start with apothem, you could start with perimeter. But to get the perimeter here, I know that the perimeter is equal to...
Is always your side length times how many sides you have. So it'd be times 6.
Okay, and 15 times 6 is going to give us?
Is going to get us 90. I think so. Let me double check. Yes.
Yeah. Sounds good. So our perimeter is 90 here.
Okay.
Now, the apothem. So this piece of our formula, we're ready to go.
So we're
just
basically
need one
halfway
piece.
done, yeah.
Okay. Now, for the apothem, I'm going to encourage you guys, when you draw in the apothem, which goes perpendicular from the center, perpendicular to that base.
And it always bisects your side length because,
Always,
yeah.
yes. So we know that each of these would be what?
7.5.
In fact, I'm going to even draw in the radius also. And I'm going to pull that little triangle just out. So that way we can take a look at that.
Now, while
little
she's doing
triangle.
that, the reason why she's doing that is because it's a right triangle. And if we are trying to find the apothem is a side length of a right triangle. And from last chapter, we learned all these different ways to find the apothem.
Right.
Or the side lengths.
Side lengths.
Yeah.
Okay, so, which was leading us towards the apothem. We just didn't even know it then.
Yes.
Now, one thing that we need to first of all determine is because we really only have one side right now of this triangle. But we can find something else within this triangle. Okay? We can find, we need the apothem, so we obviously don't have that yet. We don't know the radius yet.
And we don't really need the radius in the formula, so there's no reason to find it. But
No reason to
I
find
like
it.
that she labeled that because, guys, every single time in a regular polygon, that little right triangle that's formed is formed by the apothem, the radius, and half of the side length.
Now, we actually can, though, talk about an angle measure here.
Okay.
So let's go back to our original figure, and I'm going to draw in another radius. So that way I can talk about this whole central angle.
Okay.
Now, how did I find the measure of a central angle when we had a hexagon?
Or any
For
any regular polygon. So find a central angle. You always take 360 divided by how many sides, and since there's 6 sides, so it'd be 60 degrees as a central angle. Now, is that the angle in the right triangle?
No, because if
No.
you notice, that's the whole central angle. When you draw in the apothem, though, you're going to always have half of that.
So that means if I cut that in half, you're going to have 30 degrees in this right here.
You got it. Now, I want you to think, though, if we know that this is an isosceles triangle, and you knew that this was 60, and you know that these two are congruent because it's isosceles, what kind of a triangle do you really have?
That entire triangle is going to be equalateral.
It's going to be equilateral.
Now, this isn't happening all the time, guys.
No. This is really just with a
Hexagon.
So I'm going to explore another way to actually do this without a half apothem perimeter because it's a regular hexagon.
Okay.
But first, let's go ahead and keep going with this idea. We know that we've got this 30 degrees. What does that make this?
60.
So we have a 30, 60, 90. If I know the side length, how do I get to my apothem?
Well, the 7.5 is the shorter leg of a 30, 60, 90, so the apothem would be 7.5 radical 3. Now, again, guys, this only works because this is a regular hexagon. I want to stress that. You're going to find that the central angle is not always going to be something that is going to be working as nicely.
It's going to give you a special right triangle. So now I have my apothem.
Okay.
I had my perimeter.
All right.
So area is equal to 1/2 apothem times perimeter.
So what I would do is I would do a half of 90, so that'd be 45, and then multiply that by 7.5. That gives you 337 0.5 radical 3.
0.5, yeah.
Now, that would be the exact. It doesn't have units, so we can do that. But I will tell you a lot of times these are going to have units. They're going to ask you to round, so you could round as well. Okay.
Okay, and we would call that?
It's about 584.57 units squared.
Wonderful. Now, because this was an equilateral triangle, I could have done the formula that we learned at the beginning of the lesson today, the 1/4 side squared radical 3 for the area of one triangle, and there are 6 of them, times 6.
And again, guys, I'm going to stress because we like to show this
Yes.
idea because it is convenient, but
it only
works
works
with a regular hexagon. If this was a regular pentagon, it wouldn't be the case.
Because then the central angle wouldn't be 60, so it would not be an equilateral triangle. Okay.
All right, so here's the deal. It says find the area of the regular polygon. Now, what kind of polygon is this?
This is a pentagon.
So we know we have 5 sides, right?
Mm-hmm.
Now, what are they giving you in this picture?
They're giving us a radius.
Okay, so if I'm finding the area of a regular polygon,
We don't use radius at all.
we don't use radius at all. So I'm going to write that formula down again. So we need the apothem and we need the perimeter. And we aren't given either thing for that. And we're not even given a side length like the last one, how easy it was to find the perimeter. So this is one where I want you to keep in mind. Okay, so I'm going to make a little note. This is a radius. The radius is not going to be directly used in your formula.
Right.
It allows you to find the apothem and allows you to eventually find the side length, which will help you with the perimeter. So here's what I want you to keep in mind, okay? We're going to end up dealing with right triangles, but the only way we can deal with this right triangle, this is your apothem and this is your side length, okay? The only way we can find those two things is to focus on a right triangle, either one of those, which means I need to find the central angle. Okay? Because I don't know. If I pull out just one right triangle, guys, and this is something, you won't have to draw the regular polygon all the time. Like, if it says a regular dodecagon, I wouldn't want to draw 12 sides. So that right triangle is the key. So the radius is 9. Okay? This is our apothem. This right here is half of the side length.
Right.
I want to keep that in mind. All right? So we need to find this central angle. And how do we find the central angle?
360 divided.
All right, so 360 divided by 5 gets you.
That's going to give us 72.
Now, that's this entire angle here. But we only want half of
it.
this triangle, so we're going to take half of 72.
Which would be
and that gives
36.
you 36. So that's this angle right here. Now, not as convenient as the last
Not
one.
a 30, 60, 90.
It's not a 30, 60, 90 triangle. So here's our goal. Again, our goal is to find the apothem. That's one of the sides of this right triangle, and eventually the perimeter, which means we're going to have to find this piece right here as well.
Right. So to me, it sounds like we're going to need to use some trig
And the only way the reason is because we can't use Pythagorean theorem,
because we only have one side.
and we can't use a special right triangle. So
Exactly.
trig is our option. So let's find the apothem first.
Okay. So I'm seeing from that 36-degree angle that I've got the adjacent and the hypotenuse. So I know I'm going to be using cosine.
So the cosine of 36 equals
A
A over 9. So basically, your A is going to equal whatever 9 times the cosine of 36 is.
Right, which gives us like 7.2811529, etc. So
Okay, so let's do 4 decimal places just
so
to
let's
kind
take
of.
it 1, 2.
And guys, here's the deal. We're going to have to round on this because we have to use trig. There's no way about it, okay? I
Right.
know there's no units, but when you have to use trig, we have to round, okay? And if you have to round early on, we know how to leave it in our calculator, but if you have to round, if you're not comfortable with that, round more decimals, okay? So there's your apothem, all right? So we know that. We can actually put that in. And we're going to now find the perimeter.
Okay.
Okay, now how are we going to find the perimeter? What do we got to find?
We need to find that half of the side length.
Let me call this x.
Sounds good.
All right, so we're going to find half the side. So how do we do that?
Okay. Well, there I see I've got an opposite and that my
Okay.
hypotenuse. I wouldn't want to use my adjacent because that was very rounded.
Mm-hmm.
So I'm going to go ahead and say sine of 36 is equal to x over 9.
So basically, x is going to be equal to whatever 9
9
times sine of 36.
Right. Which was 5.2 5.2901.
5.2901.
If we round.
Now, that's only this piece.
Yeah. Now, I'm leaving this in my calculator.
I love this. I love that you're leaving your calculator. Because now, our goal is to eventually find the perimeter.
Right.
So, we only know half of the side. So, to get one side, what would I have to do?
Times 2.
So, if I'm timesing that by 2, that's going to give you one side, which ends up being about
10.5801.
But we want the whole perimeter.
So now times the 5 sides.
So take that times 5 and you get
52.9007.
Now, you could do this in one step. Notice if I find half the side, but I want the perimeter, instead of just multiplying by 2 and then multiplying by 5, I could multiply this side, this half of the side by
just by 10.
And that will also get you the perimeter. Okay, if you want to just do it all in one swipe, okay?
Right.
So you're going to multiply, if I can squeeze this in. I knew I'd probably not have enough room. So is this already in our calculator? Yes. So I'm going to leave that in my calculator, and I'm going to take basically that times.
And answer times. Now, you could type in 9 cosine 36,
Again.
and that would be more exact. That's what I always do. And then take that.
And then cut that in half.
Divide by 2. And I usually get the answer first and then divide it by 2. And that would be approximately 192.59 units squared.